Hello and welcome to this lecture. This lecture is basically on a very interesting topic of bounds on probabilities or inequalities in probabilities using mean and variance. Okay, so we saw before that mean represents some sort of a center of the distribution and variance represents some sort of a spread in the distribution. It seems like vague ideas here. Can we say something more precise? Is there some precise connection to probability? It turns out not exactly, but at least we can get some good bounds on probabilities using mean and variance. This short lecture is about two such bounds, and those bounds are very powerful and very useful. Okay. So before that, we are going to use a simplified notation for mean and variance. This is very common in probability classes and statistics classes. If you know what random variable you are talking about, everybody will denote mean as mu. Okay, there is no confusion, no need to write E of x and all that. So if in any situation you see this letter, this notation mu being used, that typically will represent the mean. Same thing with sigma squared. Okay, sigma squared will always represent the variance of x if the random variable x is clear from the context. So clearly sigma is the standard deviation. Okay, so this mu and sigma you will see again and again in statistics classes and probability classes. Okay. So if there are multiple random variables, you want to refer to a particular random variable, you simply add a subscript. Okay, mu sub x is the mean of x, expected value of x. Sigma x squared is the variance of x, and sigma x is the standard deviation. Okay, so we'll use this notation from now on. It will simplify our description. Okay. So what does mean say about the distribution? Okay, so this is a question that you can ask. Okay, so I'm going to show you, throw at you a simple example, a very simple example, and then from there sort of intuitively go towards bounds on probabilities. Okay, so let's say you have a class that you took and marks were given in the final exam or something, and then the teacher said the average marks is 50 by 100. Okay, so it's a likely average mark. It looks reasonable. Okay, maybe there is a spread of students in class and you have 50 by 100. Now, suppose now I ask a probability sort of question, as in what fraction of students will have marks greater than or equal to 50? So what does this mean? So if I pick a student at random, what's the probability that their mark will be above 50? Okay, so this is sort of the question I'm asking, right? And you can sort of argue that it cannot be 0. Okay, it cannot be that nobody is greater than or equal to 50. Okay, if nobody is greater than or equal to 50, how can the average be 50, right? So average is sort of the add up everything, divide by the numbers. So it has to, some numbers have to be above or below or equal, right? It cannot be that everything is below. Then why is the average 50? It's not going to be about 50, right? It will be lesser than 50. So you notice that given the average, I can say something about the fraction of people who are above or below some number. Here is a more interesting question, maybe you have not thought about this too much. What fraction of students will have marks greater than or equal to 80? Okay, the average is 50 only. Now what fraction will be greater than or equal to 80? Okay, so here again you can't give a precise answer, but you can give a bound, right? So for instance, you can say it cannot be 1, it has to be definitely lesser than 1. Why is that? If everybody got above 80, then the average will be 80 and above, right? It's not going to be 50. If the average is 50, clearly a lot of people got less than 80, right? So here you can in fact even be more precise. It cannot even be 0.9. Think about why. Okay, so can it be 0.9? No. Okay, so no. This I will leave it as an exercise to prove why that is no, but it cannot be 0.9 also. Okay, so you'll see it will be lesser than 0.9, and there are some good bounds that you can do just based on the average. Okay, so average does say something about the distribution of the marks, and this lecture will give you a brief idea of how to use average and variance and say something about where the random variable is likely to lie. Okay. Okay, so this is also related to what is called standard units in probability. Okay, supposing you are observing some random phenomenon, and you observe an increase in that random phenomena. Let's say, I mean later on I will refer to this, but let's say you are looking at accidents in the country, number of accidents in the country. I don't know if you look at these numbers, it goes into the lakhs every day or something like that. Okay, big number of accidents happen in the country. Okay, so supposing that number is increasing. Okay, when do you get alarmed? When do you think it's a huge increase, or when do you think it's a small increase? Okay. So all of that in absolute terms, it may not be easy to see, but if you know the mean and standard deviation, then you can say something reasonable about it. Okay, so that's why this standard units is something that's very important. So supposing you look at a random variable x, it has a mean mu and a variance sigma squared. Okay, you may get values of x which are close to the mean, or it may be far away from the mean. Okay, so always you can think of this x minus mu. Okay, so what value you actually got and what is the expected value. And this x minus mu is sort of like a deviation from the expected value, right? So distance from the mean. It could be positive or negative. Okay, you can be above the mean or you can be below the mean. How far are you above the mean? Usually, the number of standard deviations you are away from the mean is computed as this standard unit. There's a good reason why that's very important. So what is the standard unit? In some sense, you're going to look at x minus mu divided by sigma. Okay, so this quantity is sort of a standard unit, and it tells you if this quantity is large, then you're really far away from the expected value. Okay, the sigma plays a very nice role. So you don't expect x minus mu by sigma to be very, very large. If it's 10 or something, then you really got an outlier. I mean, way above what you expect things to see. Okay, so x minus mu, you expect it to fall between minus c sigma and plus c sigma. Okay, it has to be within a certain multiple of sigma. You might have heard this very famous 6 sigma terminology, right? So if x minus mu is above 6 sigma, people generally consider that as being an extreme event in some sense. Okay. Anyway, so what we're going to do in this lecture is make this notion a bit more precise using bounds from probabilities. Okay, so this may be a rough notion in your head. It may be very vague, but how do you make it precise? How do you put a number on it using a couple of inequalities or bounds on probabilities using mean and variance? Okay, so we'll start with example. Okay, here's an example. Supposing you throw a pair of die and x is the sum of the two numbers. Okay, so the mean is 7 and sigma is 2.42. You can compute this. This is easy to see. Now, if you look at the probability that absolute value of x minus mu is less than or equal to sigma, right? So mu is 7, so absolute value of x minus 7 is less than or equal to 2.42. Okay, so you do that calculation, you will see x has to lie between 4.58 and 9.42. But remember, this is just integers, which means x, this is the probability that x takes values 5, 6, 7, 8, 9. Okay, and that probability will work out to 2 by 3. You can go in and compute this. Okay, so you see probability that x minus mu is greater than sigma is 1 by 3. Now, what about probability that x minus mu is greater than 2 sigma? You can do the calculation again. Maybe there's a bracket that's missing here. Okay, you will see that this is 2 by 36. And that's about 0.056. So, you see the drop between sigma and 2 sigma, the x minus mu, absolute value of x minus mu is within sigma. So, x is within mu plus sigma and mu minus sigma. That is probability 1 by 3, 2 by 3. And x is between minus 2 sigma and plus 2 sigma, that probability is 1 minus 0.056. Okay, so you're away out of 2 sigma only with very, very, very low probability. Okay, so let's look at one more case here. This is x being uniform from 1 to 100. In this case, you can compute the mean will be 50.5 and the standard deviation is about 28.9. Okay, and probability that x minus mu is greater than sigma is 58 by 100, about half, about 0.6.5. And then probability that x minus mu is greater than 2 sigma is actually 0. Okay, so you see how this probability drops. So hopefully this example sort of convinced you about that. We'll also see, like I said, precise bounds to get you upper bounds on how likely is it that the random variable deviates from its mean. Okay, the first such inequality is called Markov's inequality. It's a very famous inequality. Here is the statement: if x is a discrete random variable taking non-negative values with a finite mean, the mean has to be finite. It cannot be one of those infinite non-existing cases. Okay, it has to be finite. Then probability that x is greater than or equal to c is less than or equal to mu by c. Okay, so this is a very simple inequality. If you know the mean, so and then x is greater than or equal to c is less than or equal to mu by c. But remember, x has to be non-negative. Okay, so this is very, very important. The range of x has to be non-negative. X cannot take negative values. This applies only when x is positive. Okay, so a very easy example. Supposing you take c to be 100 mu. Okay, then probability that x is greater than or equal to 100 mu is less than or equal to 1 by 100, right, which is 0.01. Okay, so already you see a bound here. It may not be a great bound, but still you get a bound. It cannot be very away from the mean. If it's less than 1%, likely to be 100 times the mean. Okay, so simple inequality, it only needs the mean. It's a very powerful idea, by the way. This is used quite often in so many other derivations. The proof is here. I'm not going to go over the proof. It's quite simple. Let's just add it up and define the event and observe that if it's greater than c, you can, instead of t, you can use c here and you will get it. It's quite an easy proof, but it's an easy inequality to remember as well. Probability that x is greater than or equal to c is less than or equal to mu by c. But remember, this holds only when x is non-negative. If the range of x has a negative value, then this does not hold. Okay, remember that. It's very important. The next inequality is called Chebyshev's inequality. It sounds very fancy, but it's a very simple inequality. For this, you need a finite mean and a finite variance. Okay, so x is a discrete random variable, finite mean, finite variance, then probability that x minus mu is greater than or equal to k sigma is less than or equal to 1 by k squared. Okay, so this is sort of exactly what we are looking for, right? I know mod x minus mu is between minus k sigma and plus k sigma. I expect with k that the probability that it goes out will be lesser. How does it fall? It falls as 1 by k squared. Probability that mod x minus mu is greater than or equal to k sigma is less than or equal to 1 by k square of k. Okay. Proof is just using Markov's inequality. That's why Markov's inequality is powerful. You use it to x minus mu whole squared, you will get this. I'm not going to go into the detail, but using this inequality is what's important. Okay, so there are other forms, numerous other forms you can manipulate it. Instead of writing k sigma, you can write it as c. If you write it as c, then you will get k will become c by sigma. So you get less than or equal to sigma squared by c squared. Instead of writing mod x minus mu is greater than or equal to k mu, you can simply write it as x minus mu whole squared is greater than or equal to k sigma squared. You can see how Markov inequality applies, right? So this is a non-negative random variable. Okay, even whether x is negative or not, right? See, okay, so I forgot to mention that important thing. So Chebyshev's inequality does not need x to be non-negative. Okay, x could be positive, x could be negative. This always holds. It needs to have a finite mean and a finite variance. So you can see how the proof has gone. You instead of x minus x, you look at x minus mu whole squared. Okay, that's a non-negative random variable. You can use Markov's inequality, right? So this is just Markov. Okay, why? Because expected value of x minus mu whole squared is sigma squared, right? Probability that this non-negative random variable is greater than or equal to k squared times sigma squared is less than or equal to 1 by k squared. So Chebyshev's inequality is actually Markov's inequality applied on a slightly different random variable. It's not all that different. Okay, so Markov's inequality is really the fundamental one in some sense. Okay, so people also write it like this, x minus mu greater than or equal to k sigma, absolute value x minus mu greater than or equal to k sigma is the same as x being between mu plus sigma and mu minus k sigma, right? So that probability, okay, so if x minus mu is less than or equal to k sigma, that probability is greater than or equal to 1 minus 1 by k squared, right? See, this is the complement of that, right? This guy is the complement of mod x minus mu greater than or equal to k sigma. Okay. So another way to write this, see, remember x mod x minus mu is greater than or equal to k sigma happens in two cases. The first case is x is greater than or equal to mu plus k sigma, or x is less than or equal to mu minus k sigma. Okay, these two are non-overlapping events. Okay, they are not mutually exclusive. So this probability can also be written as probability that x is greater than or equal to mu plus k sigma plus probability of x is less than or equal to mu minus k sigma, that is less than or equal to 1 by k squared. Okay, so if the sum of these two probabilities is less than or equal to 1 by k squared, each of them better be less than or equal to 1 by k squared. Okay, so these are all the different forms in which you can use Chebyshev's inequality. Is the same thing written again and again in different ways, and hopefully you see why this is just the Markov's inequality, right, applied to x minus mu whole squared. Okay, so it's very powerful. It tells you how x is sort of, it's around its mean and in the units of sigma. Okay, so let's take a few distributions and compute random variable mean and variance and the actual probability. You will see how Chebyshev inequality may be actually quite loose. Okay, mod x minus mu greater than or equal to 2 sigma is less than or equal to 1 by 4, isn't it? We know that it's 0.25. But if you take binomial 10 comma half and compute mu as 5 and sigma as about 1.58, if you actually do this probability calculation, probability of mod x minus 5 greater than or equal to 2 sigma, you see probability that x needs to be in 0, 1, 9 or 10, and that is 0.021. It's much smaller than Chebyshev inequality, and there are reasons for why this is true, but at least the inequality holds. We know that the inequality is true. This is definitely less than or equal to 1 by 4, okay, of course. If you take the geometric random variable of 1 by 4 parameter, we know mu is 4 and sigma is 3.46. It's a calculation you can do. And if you do probability that mod x minus 4 is greater than or equal to 2 sigma, this is the probability that x belongs to 11, 12, 13, 14, etc. on that side, okay, and that is roughly about 0.056. Once again, this ends up being less than 1 by 4, okay. So you can check that the actual probability really satisfies Chebyshev's inequality. Maybe it's far away from the bound predicted by Chebyshev's inequality, but at least it satisfies the bound, okay. All right, so let me conclude this little lecture by talking about what mean and variance say about the distribution. So clearly, by Markov's inequality, the mean itself can be used to bound how far the non-negative random variable can be above its mean. Okay, so that we have seen. If you given mean and the standard deviation, and Chebyshev's inequality gives you a very nice bound on the probability that x minus mu goes above k sigma or below minus k sigma, right. So x is greater than mu plus k sigma, or x is less than mu minus k sigma, that is bounded as 1 by k squared. Very nice expression, okay. So mean and variance through these bounds give you a very nice characterization of how much a random variable has really deviated from its center, okay. So here is a simple example I am giving you. Look it up and see if you can answer this question, okay. Supposing the average number of accidents decreases by 10,000 per day, okay. So number of accidents, is that a significant decrease? How do you answer that question? You have to look at the standard deviation, right? How much has the decrease been, okay. So let me not say average, the number of accidents decreases by 10,000 per day across the country, then is that a significant decrease? Okay, so to answer that question, you have to see what the standard deviation is, and if that ends up being, if 10,000, actually if you look at it, it's not that high. So I think the number of accidents, average number of accidents in the country is about a few lakhs, if I'm not wrong. It's very high. So 10,000 doesn't sound that big, at least from Markov's inequality, but you have to really look at the standard deviation, and then you'll see is that a sharp decrease. I mean, if it's a very high decrease, then we are doing something right, we are doing some good policy to prevent road accidents and all that. If it's a minor decrease, you're going to think of it as naturally something has happened, okay. So this kind of understanding comes from mean and variance, and they give you very useful bounds on the probability itself, okay. Thank you very much.